Hi, welcome to week 3 of social network analysis. This week we'll be tackling centrality. Centrality tells us which nodes are important in the network. This goes beyond just looking at social networks and which nodes might be popular, and to looking at all sorts of different networks, trade networks, who are the most important importers, exporters, nodes that bridge different regions and facilitate trade. In biological networks, which genes, for example, play a very crucial role in regulating entire systems and processes. In infrastructure networks, which nodes are critical, such that if you were to remove them, you would significantly impede the functioning of whatever the network is supposed to do. So identifying such important nodes is pretty critical, and it may be one of the first things you want to do when you look at a network is look at what nodes are most central. If you go to the website moviegalaxies.com, what you'll see are a bunch of networks that have been constructed out of the scripts. So they parse, I'm guessing automatically, through the scripts and see this character address this other character at this point in the movie script, so let's draw an edge. So if you look at, for example, the 1993 movie The Fugitive, you can see immediately that there's this central node here, Kimball, and this is Dr. Richard Kimball, who is the fugitive, falsely convicted of murdering his wife. And you see here a secondary important individual who is Deputy Gerard from the U.S. Marshal Service, who is pursuing Kimball throughout the movie. And this you can immediately infer without ever having seen them. Well, you can't infer all those details, but you can infer that both Kimball and Gerard are central actors. Similarly, if you look at Heat, you see a similar pattern where Detective Hannah is pursuing Neil, who's like a longtime crook, right? And you start to see these kinds of patterns. Now, of course, if the movie just has one central actor, for example, in Memento, there's just Leonard, and he's the most central. So even though he may not actually remember having all of these edges, all these interactions, because what happens is he keeps losing his memory, we can see, in fact, that over the course of the movie, he's the most central actor. The question is, though, is counting edges enough? So what I'm showing you here is a fragment of the network, my first social network that I ever gathered data for. And these were Stanford homepages. So take yourself back to 1999. This was before Friendster, before Facebook, before MySpace, really. People were still constructing social networks online in the best way that they knew how, which was to link their home pages together. And the way that I caught on to this was that, this was actually back in my undergrad days. A friend of mine had linked from her homepage to mine and said, "Hey, Wada, how come you're not linking back to me?" And so I started, actually, my homepage had a friend's page that linked to my friends. And once I was at Stanford and in grad school and starting to study networks, I grew curious, how many people actually did this. And so I gathered the data, and this is the my local network neighborhood in the Stanford homepages. I linked to Orkut Büyükoktin, who here looks very central. He is also linked to or links to many other friends, and in fact, he was sort of the center of my social universe in graduate school. Now, the complete picture, though, is something like this, right? So, sure, if you look at degree, Orkut may be one of the highest degree individuals in the network, but still you would probably say that he's peripheral to this whole network. However, that didn't last long because Orkut actually created Club Nexus, which was it had exactly the same functionality as Facebook, was created around the same time as Facebook, but was for Stanford students. And there he definitely was the center of the network. Then when he eventually started working for Google, he created their first social networking service that was called Orkut.com and was incredibly, successful there. So much so that, where that service flourished was especially in Brazil and in India. And so when he went to Brazil, he actually needed a security detail. He'd become so very central thanks to starting this hugely popular social network. But back to this picture, it tells us that back in 1999, when Orkut was still a new grad student, maybe his close friends had come to appreciate him, but he was still not the center of the Stanford social life. So what kinds of centrality measures could we use in order to make that distinction? So there are many different notions of centrality. We talked about in degree and out degree before, and we'll review them, but there are also notions of betweenness, closeness, and we'll also talk about eigenvector centrality. So in degree is just the number of incoming edges that a node has, and here x has higher in degree than y happens to have in degree 0. I have here plotted the network of oil exports using the NBR United Nations trade data. In fact, I think they base the data on imports rather than exports, but you can because they consider them more reliable, but you can kind of symmetrize the two. And I use the category that corresponds to petroleum and petroleum products. And you can see this, every node is a country, and there's a directed edge from the exporter to the importer. So just to check your understanding, which countries have high in degree? That is, they import petroleum and petroleum products from many others. Now let's talk about out degree. Out degree is just the number of edges that emanate from a particular node. So here I have just modified the same network of oil trade, and I have sized the nodes by their exports, and I've also colored according to the ratio of exports to imports. So if that ratio is high, the node is more blue. If that ratio is low, the node is more red. So for example, here, the US imports much more than it exports. So just to see if we know what's going on, which country has low out degree but exports a significant quantity of petroleum products? In this first visualization, you may have seen Singapore actually have a non-significant out degree. And that's a little bit puzzling because Singapore is a city-state. So where is it getting this oil to export? So what I've done is I have excluded, everything except for crude petroleum, that is the actual oil as opposed to derivative products. And here you can see that Singapore becomes primarily an importer. It has in degree, but it doesn't really have significant out degree. So this illustrates the point that it's when you're talking about centrality, it's very important to know first, what does your network represent? What is its scope? Here, scope is not that much of an issue because we have all countries. However, what exactly do the edges mean? Is it crude oil or is it refined oil? Even little tweaks can make a significant difference. So you just have to know what your network is, and when you're talking to others, you have to honestly represent that as well. So let's put some numbers to it. Let's quantify centrality. And let's switch to an undirected mode in networks for the time being. So in undirected degree, all we're doing is we're counting the number of edges you have. So if it's a friendship graph, it just counts the number of friends. And the basic assumption here is that it doesn't matter how many friends your friends have or anything else. You're just counting the number. That's all that counts. You can normalize this measure by dividing by the maximum number possible for the degree, which is n-1, as we saw just last week. So Here, this node has a normalized centrality of 0.5 because it's connected to 3 of the possible 6 other nodes that are in the network. And although I personally don't normalize centrality degree that often, you will just for my own purposes, I like having the raw count, and especially with large networks, it's you have a network of 1 million nodes. No one's going to have all the normalized degree centralities are going to be 0.000, right? Because you're not going to be connected to all the other nodes. That's ridiculous. But a lot of social network analysis software does like to normalize. So I would just like you to get used to these normalized scores. And of course, you can just multiply by n-1 to get the degree back, the number of neighbors for each node. Centrality refers to an individual node, but there is a network-wide measure called centralization that characterizes the entire network, and what it does is it captures the inequality in the distribution of centrality. So it could be the inequality of degree between the nodes. And for this, it doesn't matter that much what particular measure of centralization you use. You could just use the standard deviation in degree. And I have used this, for example, when studying trading networks for commodity futures contracts, right? We just looked at standard deviation in degree, but we also threw in something called the Gini coefficient, which varies from 0 if everyone has the same degree to 1 if one node has all the degree and all the other nodes have degree 0, which you might see in a star formation. There's also Freeman's general formula for centralization, and what you look at there is you sum over all the nodes, you take the maximum value that you observe in the network, you subtract the centrality of that particular node, and you do this for all the nodes, and then you normalize by this number of pairs, right? And it's just one lower because you get zeros for the node that has the highest centrality. So let's look at a few examples. This is with Freeman centralization. Here, as promised in the star formation, you have perfect centralization. You get 1.0. Here in the line graph, the nodes look pretty similar as far as degree is concerned. We'll see later that using other centrality measures, right, the one that's in the middle might end up being more central, but here all we're doing is counting degree, so all these nodes look pretty similar, giving us a relatively low centralization value. And a similar thing happens for this kind of butterfly network where, again, the nodes have either degree 2 or 3, and it's all very similar. I mentioned these trading networks that I had analyzed. So these are brokers, and they're trading in futures contracts having to do with the S&P 500. And in this case, what I've done is I've sized the nodes by their in degree. So the larger the node appears, the higher its in degree. And I've colored them by out degree. So the larger the out degree, the darker the node. And in any case, you can see that here the network has very high in centralization because one node really dominates. It has a very high in degree, and most of the others have relatively even in degree and lower in degree. And here on the right, you see that actually all the nodes have relatively even in degree, and no one is really hogging all the end links. So there's an example where we could actually use centralization of the whole network and correlate it with other variables, for example, the returns and volume and other kind of financial properties of the system at that time. But let's return to this question of things that simply counting the number of edges doesn't capture. if we look at this graph, degree may very well capture what's going on. But if we look at this network, right, this node has degree 2, which makes it kind of less important in a degree sense than these two nodes, and about of equal importance as these two nodes. But intuitively we think that this node must be important because everyone here who may want to get in touch with anyone here is going to have to go through this node. So how would one capture that? Similarly here, degree says all of these are equal, but this one, if it wanted to visit any of the other nodes, it would just make 2 hops max, and all the other nodes would potentially have to make 3 or 4 hops if they want to reach some of the individuals in the network. So how do we capture that? Well, let's return to the Stanford Social Web, right? Here again, we have that ORCUD is very central locally. And certainly for my social neighborhood, if any of us wanted to get in touch with the undergrads and so on, maybe ORCUD would be our best choice, and he would kind of be between us and the rest of the network. But overall, his betweenness might not be as high as, for example, some of the other nodes kind of closer in, and his closeness, in a sense that he's not very proximate to the rest of the network, should be low as well. So let's first talk about brokerage. This is where a node lies between other people. Here X plays more of a brokerage role than Y because these two nodes would have to go through X to talk to these two nodes. And there is a bunch of research into this. In particular, Ron Burt at the University of Chicago Business School has studied what advantages individuals who occupy such roles might have. And he's found things such as they're more likely to generate creative ideas. If he studies them within an organizational context, their ideas are more likely to be accepted, they're more likely to receive favorable reviews, and they're more likely to be credited. Now, of course, there's a little bit of an ambiguity. Is it that the person enjoys these advantages because they occupy that position in the network, or did they come to occupy that position because they're a special kind of person who does generate creative ideas, etc., right? And this is a little bit of an ongoing debate. The consensus seems to be that if you put someone incompetent in that position, they're not going to suddenly start to blossom and do really, really well. But if you have a good person in that position, they're in an even better position, or can accomplish even more when they're in the brokerage position. And this goes back to the notion of constraint. And that is that if you are not a broker, you experience constraint in the sense that your contacts are talking to each other, which means that you can't say one thing to one and another thing to another because they're communicating with each other. And so you're constrained in what you might be able to pull off. On the other hand, if you're in this brokerage position, you can turn to one part of your network and say, hey, I would do business only with you. And they have no reason not to believe you, but you could turn around and to the other side of the network that you're kind of bridging, and you can say, oh, you guys are my favorites, and no one would be the wiser. And so this is what's called, like when you're a brokerage position, you actually experience low constraint. So let's look at this measure of betweenness, which is going to capture brokerage. The basic idea is that you're asking how many pairs of individuals in the network would be connected through you on their shortest path to each other. So are you on the shortest path between those other two nodes? And it's possible for there to be multiple short paths. In that case, what you're going to get, so here you're I, and you are on one of the shortest paths between J and K, or one or more of the shortest paths between J and K, but the credit you get is the number of shortest paths that you're on divided by the number of shortest paths that J and K have. And then your betweenness is the sum over all pairs of nodes JK. And you can normalize this. Again, for betweenness, it might make more sense because these values can indeed become very astronomical. But you're just normalizing by the number of pairs of vertices, excluding I itself. So for what fraction of the other nodes are you on the short path? So let's look at a few examples on toy networks. Here, the central node has betweenness 10 because there are 5 times 4 divided by 2, because we don't care about direction, different pairs that go through the central node in order to reach one another. But each one of those nodes individually has betweenness 0 because no one has to go through them to get to anyone else. So let's return to our line graph. And here, naturally, A has 0 betweenness because it's not on the path between any other nodes. B has betweenness 3 because A relies on it to reach every one of the 3 other nodes. C has betweenness 4 because it is on the path between A and B and D and E. Note that in this case, C gets full credit because there are no alternate paths, for example, between B and D. The only way they can reach each other is through C. If we go back to the butterfly network, remember this central node had degree 2. Now it has the highest betweenness. It has betweenness 9 because each of these 3 nodes relies on the center node in order to reach the other 3 nodes in the network. On the other hand, these peripheral nodes here have betweenness 0 because you wouldn't go out of your way in order to reach any of the other nodes. They are on no shortest paths. Let's look at this particular toy network. Here, C and D each have betweenness 1. How do you calculate that? Well, C is on the path from A and B to E, and so is D. So imagine first that D is not there. Well, if that were the case, then C would have betweenness 2 because it's on the path from A to E and on the path from B to E. However, D is on the exact same paths, and so they share credit and they each get betweenness 1. Quiz question: what is the betweenness of node E? Here's an older version of my Facebook network. I've sized the nodes by degree. The larger the size, the higher the degree, and I've colored them by betweenness. The redder the node, the higher the betweenness. And you can see some nodes here that have relatively low degree, but they have high betweenness because they bridge, for example, my undergrad network with my University of Michigan and research network. Another quiz question. Find a node that has high betweenness but low degree. And now find a node that has low betweenness but high degree. What if it's not so important to have so many direct friends? So it doesn't matter whether you want to do this power play where you're brokering between different parts of the network and you want to make sure that they have to go through you. What if instead all you want is that you have easy access to a large part of the network? You want information to reach you in a short number of hops. You want to be able to disseminate the information that you have. And therefore, it's not about brokerage, it's about how far away the rest of the network is from you. For example, in this network, this node has degree 1, but because it's friends with the highest degree node, this means that the number of hops from it to anyone else in the network is only 1 extra hop than it is for the most central node. It in fact has easy access through just that single connection. So we want to capture this notion of a small number of hops. So by definition, the closeness centrality is the sum of the distances between the node in question, I, and all other nodes, j. And you're going to sum these distances and invert them. Now there's a problem in that if your node has multiple connected components, that is, there are nodes in other components than yours, your distance to them is infinite. And when you sum infinity with other things, it means your closeness is actually zero, right? Because here you're inverting. So in order to avoid that, an alternative measure of closeness is to take this inversion inside of the sum. And so you take the inverse of the distance to every other node and you sum those values. So all those nodes and other components, they just contribute zero to your closeness, but you do get credit for having short paths to nodes that are in your same component. And you can normalize this by n-1, the number of other nodes in the network. Here is a toy example where if we look at the closeness of A, it has distance 1 to B, distance 2 to C, 3 to D, 4 to E. We sum those, we divide by n-1, and we invert, getting a closeness of 0.4. Finally, we can also look at our other toy networks, and here again, the middle node has high closeness. The ones right next to it also have relatively high closeness. Here the middle node has high closeness, but the other nodes being directly connected to this hub, that is the spokes, they actually have relatively high closeness as well. They're only 2 hops away from any other node. So looking at this network, can you tell me which node has relatively high degree but low closeness? When you look at a real-world network, such as my Facebook network, it's clear that the nodes with high closeness are close to other nodes with high closeness. That is, they're kind of in the middle, in the thick of things. And in general, we may want a definition of closeness, a separate centrality measure, which we're going to call eigenvector centrality, which says that you are as important as your neighbors are, and your neighbors are as important as their neighbors are. So it's this nice recursive definition. So if we have node I and we have its neighbors and the weights of the edges, then the importance of I is going to be the sum of these kinds of terms where we take the weight of that edge, and normally it's 1, but you can use weighted networks as well, times whatever the centrality of that node is. And you may iterate this many, many times because, of course, as you're calculating the centrality for I, it's going to actually now affect the centrality of K, etc. And this is precisely the problem of solving for the eigenvector of the adjacency matrix with eigenvalue 1, and that's why it's called eigenvector centrality. One of the first people to apply eigenvector centrality to social networks was Bonacic. He wasn't happy with just, the plain adjacency matrix. He wanted a parameter that he could vary, and he chose this parameter beta. And what beta does is it says, how important is it that your neighbors are important versus just how many neighbors you have. So he was able to tune that. And this parameter alpha here is just a normalization constant. So you have that the centrality of node I for a certain parameter beta is the sum over all of its neighbors, which you're going to get from this, the adjacency matrix. This can be weighted or not. For each of those neighbors, you're going to have this factor of alpha plus beta times the eigenvector centrality of the neighbor. And this can be solved through a matrix computation to derive the eigenvector centrality scores for all the nodes. Now, you don't have to sit there and calculate this by hand. That could get really hairy. And naturally, a lot of software can calculate these kinds of things for you, but it's good to know where it comes from, what the idea behind having such a centrality measure is. And so if you have small beta, what happens is, beta close to 0, is that only your immediate friends are going to matter. So it's going to be how many friends you have as opposed to how important they are, because their importance is derived from the structure of the wider network. If you have high beta, you're going to have low attenuation, meaning that all of those multiple steps are going to be quite important. It's not just how important your friends are, but also how important their friends are, the friends of friends of friends, etc. And in the case that beta is 0, you're just recovering the degree centrality because all you have is the sum of the edges for a node. The interesting thing that Bonicic started examining was what happens if beta is actually negative. So when beta is positive, um, the centrality follows the intuition I said, which is that having neighbors who are themselves important makes you important. However, if beta is negative, nodes have higher centrality when they're connected to actually less central nodes. So let's see if this made sense to you. Take a look at these two networks and try to figure out which one has beta positive and which one has beta negative. So far, with the exception of degree, where we had in degree and out degree, we were talking primarily about undirected networks. And I just wanted to take a little bit of time to talk about centrality in directed networks. There naturally are many different directed networks, for example, the World Wide Web, and we mentioned how the meaning of out degree, how many different pages a page points to, is really different from the meaning of in degree, how many pages point to it. So out degree just indicates, okay, is this page referencing a lot of different content? In degree is a signal of how many other people found that content relevant, enough so to link to that page from their page. Food webs, naturally directed, right? The wolf eats the sheep, not vice versa. Population dynamics, where individuals migrate, right? Migration patterns are usually directed. Influence, how much you influence someone is probably different from how much they influence you, and it depends on your relative prestige and the nature of the relationship. Hereditary networks, citation networks, biological networks, such as transcription regulation networks or neural networks, are also directed. And it makes a lot of sense, right? If you have a task to do, then some nodes are going to affect the behavior of other nodes, and the network is directed. If it was undirected, things would be just firing back and forth. Some of the measures are just naturally extended into their directed counterparts. So if you remember when we talked about betweenness, this was simply the number of paths between all the other pairs of nodes that pass through our node of interest divided by the total number of paths that those pairs have. And what we're going to do is we're just going to change it. We're going to say instead of undirected paths, these are going to be directed paths. And when we normalize, we're going to have here n minus 1 times n minus 2, and we're going to lose that factor of 2 because getting from A to B can in fact be, or actually here from K to J, can be different than getting back to K from J. Right, so we do need to take into account the directionality of the path, but pretty much directed betweenness follows its undirected counterpart. Same thing with closeness centrality. You can talk about in closeness or out closeness, and typically you will only consider vertices that are reachable. So this is kind of getting, because once you have a directed network, it's even more difficult for everything to be connected, because if you have the same number of edges and they're directed, you're in fact, and you can only traverse them in one direction, right? You have about half the number of edges. So perhaps you're only calculating closeness for from the reachable nodes. And here, you have the kind of input domain are going to be all the nodes that can reach you. And the question is going to be how many hops does it take? And kind of the output domain are all the nodes that you can reach in an outward fashion. So again, it's very easily extended. Where things get really I don't know if interesting is the right word, but where there was really a big game change um, I, when you added directionality to eigenvector centrality. And this was applied by Larry Page and Sergey Brin when they were graduate students at Stanford to the web. They just said, we're going to figure out how important each web page is, and we're not going to take just um, the number of other pages that point to it. We're going to instead look at the importance of those pages in a recursive way. And so, for example, here, at least at that time, Slashdot was really important. Lots and lots of other pages pointed to it. So it was enough for Slashdot to link to mention another page, and oftentimes that web server would just be brought down from all the traffic and attention that would ensue. And so we really want to capture this. It's not just random web pages that link to you, but whether those pages themselves are important. Now, there's an analogy here, which is that when you're calculating this eigenvector, it's as if you're doing a random walk. And so I like to think of it as a drunk who's kind of like wandering around, and every time he hits a node, he says, oh, okay, I'm just going to turn left and turn right. And so he's just following edges at random. And what PageRank, being the amount of time that he is going to spend at each node, what it then corresponds to is the eigenvector of the adjacency matrix. But there's a very important tweak. If this network, say the web, was undirected, the drunk could just kind of, go dip, 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 and then just go back the same way if he gets stuck somewhere. But when the network is directed, he can only follow the edges in a certain direction, meaning that here, if there is a cycle of this sort, he would just be trapped and circling here indefinitely, which then means that you actually can't compute the eigenvector, right? Because your random walker, your drunk, is actually being absorbed in different parts of the network. So the very cool insight that these two guys, Page and Brin, had was to allow for random teleportation, which is that with some probability the drunk is going to follow an edge when he arrives at a node, but with 1 minus that probability, he's just going to teleport to a random node in the graph. And this solves the problem of getting stuck, but it still captures this, the important pages are the ones that are linked to by important pages. So great. So let's see what this would look like on a simple toy network. Let's say the random walker starts at node 1. At the next step, he, with some substantial probability, will go to either 7 or 8, but we also have a 20% teleportation probability, which means that the 80% of going to 7 and 8 will be evenly split between them. So if we start out with 10 units to distribute, we get 4 each at 7 and 8, but we also distributed 20% evenly among all the nodes, including node 1. And so after the first step, we have most of the probability being at 7 and 8, but also he could have teleported elsewhere in the network. If we go on and look at what happens after 10 steps, you find that there's a lot of probability around 7, and this indeed makes sense because 7 not only has high in degree, but some of those nodes like 2 and 5 and 6 actually have other nodes feeding into them, and so recursively 7 should have high PageRank. To check your understanding, I'd like you to go to this PageRank demo where you will be moving a slider to adjust the teleportation probability, and then you're going to iterate. So you're going to distribute the probability kind of like with each step that the random walker might take. And then I'd like you to figure out whether higher or lower teleportation probability leads to more equal or less equal distribution of PageRank centrality scores. Just to wrap up for now, we've seen lots and lots of definitions of different centrality values. We had degree, we had betweenness, we had closeness, we had eigenvector centrality, and we even had sort of network-wide measures of centralization. Does everyone have approximately the same degree, or is it really skewed? We extended this to directed networks. To see, when direction matters, how do these centrality metrics translate? And what might be missing from all of this actually is an understanding of, what is this good for? I mean, sometimes it's true. It's just nice to look at a network and say, oh, here are the central nodes. For example, you can do this with the Enron email network that was released as part of the court proceedings. And you can infer who the top level management was simply because of their high centrality. And it's not entirely trivial because, sometimes the very top people don't email the most. Sometimes the people who are very central are the ones who kind of handle email on their behalf or are in charge of their calendar. So there are lots of interesting things to explore if you want to do exploratory data analysis. But if you are, and I should say in the assignment, you'll be looking at actually a court case network, and this was an antitrust case where several turbine and other kind of power generator equipment manufacturers were accused of basically colluding, doing price setting. And the question is, how does an individual's position in this collusion network correlate with their probability of, or actually their outcome, that is whether they were convicted or not and how heavy their sentence was. So that's kind of cool, right? If you could ahead of time figure out how things will play out for a conspiracy network. The other paper that you'll be looking at is, it's this remarkable data set that Sinan Aral and Marshall Van Alstyne collected of personnel in a headhunting firm. And what they discovered was that it didn't matter how fat your Rolodex is, that is how many people's addresses that it's in fact your positioning in the network, the diversity of your contacts, having less constraint that correlates both with your performance, that is how much money you bring into the company, and interestingly with the information that reaches you, whether you find out new information more quickly than your colleagues do. So I hope that those two papers, which will be part of your assignment, will be interesting. And in the next video, what I'll do is just talk about some research I've done and how I've made use of centrality measures in a very practical way. As promised, I'm going to be telling you about some applications of network centrality that I actually did myself. The first is a hospital patient transfer network. There are thousands of transfers between hospitals in the United States, and my colleague Jack Iwashnia was doing this study based on Medicare records. So people who are on Medicare, who constitute roughly half to 60% of these transfers, when they transfer between hospitals, there's a record of it, and he was analyzing this data set. It makes for a very pretty network, but it also highlights a potential problem, and that is that there are these highly resistant bacteria that sometimes take hold in hospitals, and they're because of their drug resistance, it's very, very difficult to treat patients who acquire these infections, and it's actually rather costly, right? Because your first line of defense, the antibiotic, will not work. And there's some documented evidence that patient transfers have led to also transfers of these bacteria who were hitching a ride with the patients when going to a new hospital. Now, pretty much it's each hospital trying to prevent these infections on their own. So measures that they can take, for example, are keeping an incoming patient in a separate area, and when someone enters this area, they have to be wearing masks, they have to wear gloves, they have to follow protocol. Of course, this actually costs quite a bit of money. So the question is, could you formulate more effective infection prevention strategies if the hospitals could actually coordinate within this network and pool their resources and put prevention resources at hospitals where the total number of infections across all hospitals would be minimized if you did the allocation correctly. Now, what we assumed was that the more resource a hospital has, the less likely it is to acquire an infection. But once it's infected, it can't really root out such an infection, and it will actually be sending along infected patients to neighboring hospitals. So, one solution, of course, would be to forbid all patient transfers. However, there are many benefits to such transfers, starting from some hospitals being overbooked. Their intensive care unit can't take any more patients, and so they transfer to a second hospital, or a hospital doesn't have the needed expertise and a neighboring hospital does. And in general, patient outcomes are better when patients who need to be transferred are transferred. So we really do just want to allocate some prevention resources as opposed to, shutting down whole hospitals or something like that, or forbidding transfers. So there are different strategies that you could use. You could just allocate money at random. And here what this shows is what the number of infections would look like after a year. And so you can see that there are really some hotspots, some hospitals that would have been very likely to be infected if an infection started at any random hospital. So you say, well, okay, we know that some hospitals have more transfers than others. And so we tried a strategy that would target those hospitals with high degree. And here, we have the choice of in degree and out degree. Some hospitals receive more patients, some hospitals send more out. And what we found was most effective was to take the geometric mean, that is the in degree times the out degree, and the square root of that quantity. And you can see that this produces a significant reduction in infection rates. However, we also know about betweenness, right? And we know that if a hospital is sort of bridging, say, the East and West Coast, then being able to, target those hospitals that are kind of between a lot of other hospitals, that might be even more effective. And indeed it is. When you target based on betweenness as opposed to degree, you reduce infections even further. And finally, what is most effective is actually simulating the infection spread and running a greedy algorithm to see which hospitals should be targeted. And these typically are high degree and high betweenness hospitals, but you can do even better by simulating in this greedy manner. And a collaborator of mine at CMU, Aditya Prakash, actually showed that an eigenvector approach was most effective. It was a really good approximation to this greedy algorithm. And so we kind of ran the full gamut from degree to betweenness to eigenvector in solving this problem. Of course, I'm saying solving, it's kind of solved in theory. Of course, from a practical policy standpoint, it's not clear how you would get hospitals at a national level to pool resources. But still, it's an interesting thing to consider if there are, for example, federal funds that can be allocated between different hospitals. The second example I've already mentioned a little bit when we were talking about preferential attachment and scale-free networks. And this was identifying expertise in online question and answer forums. And the reason why we may want to identify expertise is that there's this response time gap between when an expert asks a question in Sun's Java forum, they may be waiting for hours or days, but when a newbie asks a question, their question is answered right away. And the question is, could you speed this up by matching experts with questions that were posed by experts in order to get those taken care of sooner? And so what we did was we gathered a whole lot of data from Sun's Java forum, and we had what is this, 200,000 users and 800,000 edges, so plenty to play with. But with real world data, the thing is always you have to decide how you're going to construct the network. So you could construct it in an unweighted way. What we wanted to do was have, for example, if you have A who posted 2 questions, and then you have B and C who answered those questions, you have some choice. You could, for example, do an unweighted network where A has directed edges to B and C, and in this case, we're saying B is more expert than A because they could answer the question. We could weigh the edges by the number, or weight the edges, sorry, by the number of threads that the 2 nodes interacted in. We could have them share credit, so if both B and C answered a question, they would each get half weight 1/2 added to whatever other weight they had. Or we could even introduce a little bit of backflow, and this just means if you asked a question that was answered, it means that at least it was sort of a decent question. So we may have a little bit of the weight of the edge going back. Now, as I mentioned before, there's very uneven participation, especially when we look at nodes that post lots and lots of replies. And in addition to looking at these kind of individual node centralities, we can look at the whole structure of the network. And something that I haven't really discussed before is the bow tie model of the web. It's very simple. You have the strongly connected component. Remember, on the web, this means that you could actually, if you're very patient and kept clicking, get from one page to any other within that component. And then you have the in component. From this component, you can start on a web page and end up in the strongly connected component, but you can't get back out. The out component means that you can get out of the strongly connected component into this region, but you can't get back in, and then kind of other sorts of structures. And what's true of the web is that this at least a decade or more ago, was that you had this very symmetric bow tie. And the symmetry is not there. It's very skewed in Sun's Java forum because, well, you do have a strongly connected component, but it's actually relatively small. Only about 12% are interacting in such a way that they're all kind of helping each other in a generalized reciprocity kind of way. So maybe A replied to B, and B didn't reply directly to A, but B replied to C, who replied to D, etc. You have a large in component. These are people who are asking questions but not necessarily replying, or if they do reply, they didn't reply to someone in here, and so they all compose this in component. And there's a small out component. These are people who only answer but don't ask. Okay, but back to the question of centrality. As I mentioned before, it was very clear, that some nodes were very active, very central. But what we wanted to know was whether, indeed, degree was the best way to capture centrality. And so, in order to evaluate, we had human raters read the posts and judge the expertise level of the repliers. And what we found was actually a very high correlation over a number of centrality metrics between the human-rated expertise and just this, whatever centrality measures we were deriving. And so in a way that was nice because you basically couldn't mess up. You could use any measure and do really well. But what was disappointing to us was that PageRank was not the clear winner. And the reason why we had hoped that PageRank would be, a good a good centrality measure is, if you think about it, if someone is um, expert enough to answer the question of another expert who themselves has been helping others, then that kind of propagation should tell us that this expert is so much better than this other expert, etc. So the recursion thing just apparently wasn't working in this form. So we wanted to know why, and we did look at the breakdown of the human rating um, versus the kind of centrality measures we were getting, and that wasn't really telling us why PageRank wasn't performing all that awesomely. And then Jun Zhang built a simulator. So from last week, you may be familiar with, hey, sometimes just simulating how a network forms can give you insights into whether you understand the dynamics that are leading to the network, right? And the dynamics may be really the things that you're actually after. And so here the parameters were who's going to ask more often. Is it going to be the newbies or the experts? And the one that seemed to resemble more the real network, just because of the skew, was that newbies ask lots and lots of questions. And then who is going to answer whom? We wanted to have a particular matching algorithm. And so in one case, we had the best preferred. That is, no matter what the expertise of the person asking, the expert who has the most difference in expertise, that is, they're as expert as possible over what is being asked, is going to answer. And we had another model, which was the just better model, so that people who are answering would be choosing to answer questions that would be challenging to them. So if a newbie asks a question, then just the people who are a little bit more expert than newbies would be answering the newbie questions. And the top level experts would kind of save their bandwidth and only answer the questions of those who are like almost as expert as they were. And this actually led to two different kinds of topologies. In the best preferred network, you can see, so this is a circle layout where I've just ordered the nodes by the expertise that we assign them in the simulation. And you can see a lot of the questions are answered by the experts. And also, so here they're shown as larger nodes. They're more central in the network. Here with the just better, you can see that the twos are answering the ones, the threes are answering the twos, etc. And in fact, you have that the experts are kind of being pushed to the periphery of the network. And so it makes sense. So it makes sense that when we look at algorithm performance, that if the underlying dynamic is this, the best guys are always answering, which is in fact what we see, right? They're not actually discriminating, then things such as in-degree or kind of z-scores of in-degree, how much higher is the degree than what you would expect at if you had a balanced in-out degree for the different nodes, that should perform better. And so we kind of figured out what the underlying dynamics were by seeing which algorithms perform well. On the other hand, in the just better simulation, if people really were mindful of their bandwidth and matching their expertise to the level of the question, then in fact we would see here PageRank is in yellow, that the PageRank algorithm would be the one that is most predictive. So, and I haven't discussed the HITS ranking algorithm. It's also kind of a web ranking algorithm. But it's just to illustrate, there are lots and lots of different centrality measures. So in HITS, the basic definition is that you have hubs and authorities. Hubs are going to link to or point to authorities, and authorities are pointed to by good hubs, right? So you have this kind of bimodal definition, and you're going to iterate again some matrix computations. And in this case, we can figure out that if you had the just better model, a hits algorithm would not perform very well at all because most of the questions are being asked by the newbies. They're the hubs, but their questions would be answered by the, by the barely experts, right? So you would get the barely experts being ranked highest by the hits algorithm. And so we can sort of predict the hits algorithm wouldn't work in this context versus the PageRank algorithm would. And so this is just to say that you have many, many different choices of centrality measures, and sometimes it's nice to throw in the kitchen sink and see what works. If you were a social scientist, you may try several different centrality measures and you stick them into a big regression where you're trying to figure out, what specific outcomes do you care about? For example, if it's a person's well-being, does their degree centrality matter more than their betweenness centrality? If you're looking at an online community, who's going to stay active in the community? Does it matter how many contacts they have? Or does it matter that they're actually bridging different communities? For example, if they have high betweenness, what you might expect is that if one community or one subset of people starts being less active in that community, they would still have another that could potentially still be active. But on the other hand, if it's really high betweenness, they may just be bridging different groups without really finding a home in that online community. So they might be more likely to quit. So the thing is, you don't know ahead of time. Just as with the Java forum, we expected PageRank to perform well, and it didn't actually perform any better. It was actually slightly worse than just looking at these z-scores of in-degree versus out-degree. And that's a little bit of the magic of doing, especially exploratory social network analysis, that you can go in with the standard set of centrality measures, and then you really think about the problem. You really think, how can I capture, for example, with expertise, maybe it's not so much how much you answer, but do you answer a lot more than you ask, right? It sort of makes sense, right? You're sort of clueful. Maybe that's a better measure. And so it does contribute to the problem of there being lots and lots of different centrality measures, but I also think, practically speaking, it's good to customize. And you can always use the standard ones, but sometimes if you're thinking deeply about your problem, you may come up with something new and different and interesting. So in the next video, I'll be talking about how to fit power laws properly. I consider this video optional because it's going to be a little bit technical, but if you're ever going to claim that you have a scale-free network, you must watch this video and learn how to fit power laws properly, because I don't want you running around making false statements after taking my class. Okay, so I'll see you maybe in the next video then. I'm glad you've chosen to learn a little bit more about power laws. It's important that if you're going to claim that your network has, say, a power law degree distribution, that it actually does. Because if it has a power law degree distribution with an exponent, between 2 and 3, this means that things are going to spread very effectively. They're going to be different strategies in immunizing the network, and the resilience of the network to node failure, as we'll learn in a little bit, is going to be affected as well. So we don't want to claim that our network is power law if it's really not. So let's see what power laws are about. Power laws are different from the normal distribution. The normal distribution looks something like this. You have the average height for a human male, and some are taller and some are shorter. And if you look at the max to min ratio, even looking at the Guinness Book of World Records, right, the tallest man is only several times taller than the shortest man. On the other hand, if you look at a city like New York City, it's 150 times 150,000 times larger than a small town of Duffield, Virginia. We've seen this before. This is the power law distribution on a log-log scale. Oh, sorry, this is it on a linear scale where we see like this very sharp L, and here it is on a log-log scale, and we see that straight line. That's going to be our signature. You see these distributions in many different domains. And here I should just say these are cumulative distributions. So rather than looking at the probability that, for example, in the first graph, that a word occurs exactly 200 times, we're going to be looking at the proportion of words that occur 200 times or fewer. And if your distribution is really power law, then this cumulative distribution, which is going to be its integral, is also power law, with its exponent being alpha minus 1. So if we see a power law in the cumulative distribution, we're actually seeing a power law distribution. And so you can see if you look at word frequency, that is, how many times in Moby Dick did the word whale occur versus the word the. Citations, how many citations did each scientific paper receive? Web hits, this is a data set that I analyzed back when I was a grad student. Books sold among bestsellers. Telephone calls received. Now, you might imagine that this is some sort of call center that received over 100,000 calls in a single day. Earthquakes, many, many small earthquakes, a few really large earthquakes. Yet more power laws, crater diameter, peak intensity of solar flares, casualties in wars, lots of small skirmishes, and then a few really large, very costly in terms of human life wars. Income distribution, a few very rich people and lots of not so rich people. Name frequency, lots and lots of Smiths and not that many, I don't know, lots of people have less common names. Populations of cities, we just talked about that. A few mega cities and many, many small towns. The power law distribution written out, we've seen this before, is that the probability of X, say a word occurring 100 times, is equal to some constant times X to the minus alpha, where alpha is typically between 2 and 3. And if we take the log of both sides, as if we were plotting on a log-log scale, we indeed see a linear relationship between the log of the probability of observing X and the log of the value X itself. We often hear power law networks referred to as being scale-free. What this means is that the power law looks the same no matter what scale we look at. So whether it's in the range of 2 to 50 or 200 to 5,000. And this is only true of a power law distribution, because if you change X by some multiplicative constant, that probability is just going to have another constant in front. You'll also hear power laws sometimes referred to as Zipf distributions. George Kingsley Zipf was a Harvard linguistics professor who first looked at the distribution of frequencies of different words in text. And some words are much more common than others. And there are all sorts of fun models trying to figure out why this is. One such model is that you're throwing down letters at random, but you also you include the space. And so the words are generated as just random letters, and and terminated by spaces. And that actually gets pretty close, but turns out to not be the correct model. But when Ziv was looking at, say, for example, distribution of words in text or the sizes of cities, another subject he studied, he termed it in terms of the size of the rth largest city. And so he got power laws with an exponent beta. And you can actually match the two exponents, because saying the rth largest city has n inhabitants means that our cities have n or more inhabitants, right? All the others are smaller. So this is in fact our cumulative distribution. And so you can flip things around and find that beta is actually equal to 1 over alpha minus 1. So if you have a power law distribution with an exponent alpha of 2, this is true of the number of unique visitors from AOL to websites. This is a very old data set, I think 1997 or so, that I studied as a grad student. When you plot the ranked plot, you're going to get an exponent beta of 1, exactly as you would expect. There's also a kind of an 80-20 rule. So using the exponent alpha, you can actually figure out whether it's 80-20 or 90-10 or whatever else. And this is just the amount of wealth that is in the hands of the richest P proportion of the population. And for example, for wealth distribution in the US, which is getting more and more skewed, the alpha exponent is 2.1, meaning that the richest 20% of the population holds about 86% of the wealth. Now let's get to the meat of the matter, which is how do you fit power law distributions? How do you know that the degree distribution that you measured on your network is actually power law? And what you start out with is this histogram. You know, I have this many nodes with degree 1, this many nodes with degree 2, blah, 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 right? And you may think, well, it's supposed to be a straight line on a log-log plot, so what I'm going to do is I'm going to plot it on a log-log plot, and I'm just going to try and fit a line to it. And this is problematic. Well, we'll see how it's problematic. Let's first see what it looks like on an artificially generated data set. So I just generated lots and lots of random variables, but I generated them in such a way that they're distributed according to an alpha exponent of 2.5. So we're going to know that a fitting method that gets close to 2.5 is actually a better one. So we're going to start with our little linear scale plot, and you see it already seems to zero out by the time it gets to 20. And over the whole range, we just see this L, which isn't very informative. And this is it on a log-log plot, and here actually it looks pretty good. It looks like we can plot this, but there's a basic problem, which is that here we have tens of thousands of observations, right? This is something like 100,000 of the data points that are generated were, you know, the number, I guess this might be 3, right? But then where we get into numbers that are over 1,000, right, there are many missing bins, right, because we just didn't get any number of, you know, 2,373 or something like that. Maybe we didn't see that in this data set, and so we have a 0. Which, you know, you can't take the log of, so it's just missing on this plot. And each of these points becomes an individual observation versus we have 100,000 data points going into here, meaning that, you know, we should be weighting this more, but we're not if we do a simple linear regression. And in fact, what you see happening is if you do a best regression fit, it's going to be totally misled by these points out here and, you know, the missing data that isn't represented, and you're going to get an alpha fitted exponent that's way too low, right? And so here it's actually saying, oh, the alpha may be something like 1.6. which, it's not, right? We know that the data came from a distribution with alpha equals 2.5. And this is just reiterating a few bins here, many bins here, but we actually have more data here than out here. So the first solution is to bin logarithmically. That is, you want to actually get more data here. So you're going to have wider and wider bins. And they're going to start, 1, 2, 4, 8, 16, 32, or you can decide which exponent you want. And then you get these nice evenly spaced data points, which you can then fit. And if we do this, we get an alpha of 2.41, which is actually pretty decent. But what it's doing as well is it's kind of smoothing out the data and losing some information, right? When you aggregate into these bins, there may be interesting features that you're just kind of smoothing out and that you won't recognize. So the second solution is to do cumulative binning, like all those plots I showed you with solar flares and family names and so on. Those were cumulatively binned. There's no loss of information because each value captures, how many exactly do you observe, how many observations do you have of this value or lower? And so you don't have kind of zeros that are falling off or something like that. And so you can do just a regression and get this cumulative exponent, which is going to be alpha minus 1. So you'll have alpha. And that's also a fine way to do it. And here we get alpha minus 1 is 1.43, and that's much closer to the actual 2.5. So that's perfectly fine. There's also the question of where do you want to start fitting? Now, I drew from a pure power law distribution because I was generating fake data. But in reality, data isn't going to be so pure, so there may be some deviation on the lower end. For example, if you look at the number of links that different university websites get, each university gets at least some minimum number of links. So you're not going to get like the I guess from your point of view, lots of universities with only one link to their website. I mean, they wouldn't be a university if that was the case. So you may see something that's somewhat like this. So really, you just want to fit out here. You want to fit the power law there, but not be misled by the low values. So you can establish an X min, a minimum value, below which you're not going to be fitting. So if we look at, for example, citations, maybe the power law is only evident for papers that were cited at least 100 times. And so you can set X-min to be 100 and then fit the tail. There is the very, very best method, which is this max likelihood method that calculates using every one of your data points. What is, the observation that you have, the data points that you have, what is the most likely distribution? What exponent would it have that would have produced the data that you see? And if you want to use this kind of a method, you can download, and I'm going to provide the link separately, from Aaron Closette's site, and it's basically Python and R code that, you can use either one. You don't have to use both, even MATLAB code, I think, that given a data set we'll first evaluate, is this a good candidate for a power law fit versus another kind of distribution such as the log normal or the stretch exponential, etc. And then if it is a good candidate for a power law fit, what is the power law? So if you're getting really serious about characterizing your network, I would recommend doing it properly. And this is the way it's done these days. So here's some exponents for real-world data. You can see that most of them tend to be between 2 and 3, but some drop a little bit below 2. Now this is weird because these distributions would have, kind of infinite variance. So most likely they have a drop-off. The power law can't extend indefinitely. So those were different data sets that weren't networks. Many real world networks are power law. So if you look at film actors, this network is who has acted with whom in a movie. And there's a funny story around this, which is that the Sunbelt Conference, which is the annual social networking conference, had a data analysis challenge, which was to take the Internet Movie Database and plot out the network of all the actors, who has co-starred with whom, and calculate things such as who are the most central actors. And little did they realize that there's a certain kind of movie, namely pornography, that produced very high centrality actors because a single actor can kind of star in many, many movies, right? They're made at a very rapid pace, and so they until the people participating in the challenge, met up at the Sunbelt Conference and started comparing notes. No one really expected that the porn industry would be so very central in the movie collaboration graph. Anyway. There's the telephone call graph, which we already talked about, right? Who calls whom? Email networks, sexual contact networks, which we talked about as well. The World Wide Web we talked about. The physical internet, also power laws, some very large hubs. Peer-to-peer networks, so for example, for file exchanges, some computers tend to be very central in these networks. And then different kinds of biological networks where you have either metabolites or proteins interacting with each other. But it's important to note that not everything is power law. So bird species abundance is not power law. Size of wildfires is not power law, even though some wildfires are very big and many are small. Even networks that appear power law at first, especially the social ones, for example, email. If you just take who has emailed whom ever, excuse me, you may get a power law, but once you start restricting that, like the other person actually replied, or maybe there was a little bit of back and forth, like some actual interaction, it ends up being not power law because people, there are really limits to how many relationships you can maintain, and so you lose the power law property. The electrical power grid, not power law. I guess the thesaurus, there isn't really a word that could be a synonym for every other word. The networks of company directors. So this is if you look at the boards of directors of different companies. So how many other people did you jointly sit on boards with? And even very hardworking, very prominent individuals only sit on so many boards, and so they only have a limited degree in such a network. So here's just an example on the AOL visitors data set. And if we try to fit it directly, we get an alpha that's way too low. If we do exponentially wider bins, we get a seemingly reasonable slope of 2.1. But it's real data. So if we do this kind of exponential binning, we may lose information about, there's actually a little bit a deviation from a power law where we don't have that as many sites as you would expect with very low numbers of visitors. And then again, in the tail, it doesn't quite match up to the power law. And so, what you may end up doing is fitting a power law with an exponential cutoff, which just says up to this value kappa, it's a nice power law, and then after that, it starts to decay exponentially. And there could just be different reasons for this. For example, constraints such as how many people you could ever interact with, or, you can only, there are only so many individuals available to connect to, etc., right? There could be different reasons for these cutoffs. So just to wrap up, power laws are cool and intriguing, but you should make sure that your data is actually power law before you boast to others. For our next short video segment, it's my pleasure to introduce Cameron Marlowe, who is the head of the data science team at Facebook. And so the
Hi.
first question to you is, how did you first get into social network analysis?
I first got into social network analysis by taking a course with Keith Hampton at MIT on social network analysis. It was an introductory course in 2001. It was frankly, I think the best course of my life. I don't know if it was the subject matter or the teacher or both, but ever since then, I've been interested in study social networks. So that's where I got my start.
Cool. And so then you started applying it, but not immediately at Facebook.
Mm.
So what was the path there?
What was the path? So I've always been interested in social networks, but it's difficult to measure them. So one source of data has always been the web, and so I've always been interested in sort of extracting social networks from different social media and online communities. So I studied weblogs for my PhD thesis, and went on to Yahoo Research, where I studied communities such as Flickr and Delicious. But really, was attracted to come to Facebook because here the social norms of the site have produced a network which very closely resembles the real social network of humans. So a lot of the work that we do here, we can sort of extrapolate more general phenomena about how human social networks work.
Okay, so can you expand a little bit on that? What role does the social network play at Facebook, how it operates?
So it's hard to underestimate the importance of social networks in the way that people at Facebook think. So I would say that I was unique in my research and the people that I interacted with when I was at Yahoo Research. But here, everyone really thinks and operates on concepts of social networks. So just to give an example, the way that we fundamentally store data here and access it for all parts of the site are is as a graph. So most of Facebook's data is represented as nodes and edges in a very large graph of people and objects and conversation. So that it's sort of part of everyone's everyday life. And some of the social network concepts that you deal with in courses like Lada's come up, in everyday work. So, this idea that the degree distribution has a very high variance, and there are some people with lots and lots of connections, and most people have, some connections. You can't really build a service, or you can't really build a product at Facebook without taking this into to account, because some of your users are just going to have such an enormously different experience with their 5,000 friends, which we sometimes call whales here, than the average user, which has 150 or 200 friends.
Okay, thanks.
Sure.
So I guess that's that, and stay tuned for more of these clips.
Yeah.
Thanks, Cameron.
Bye.